During an action potential, ions cross back and forth across the neuron's membrane, causing electrical changes that transmit the nerve impulse. The stimulus causes sodium channels in the neuron's membrane to open, allowing the Na ions that were outside the membrane to rush into the cell. The sodium channels are called gated ion channels because they can open and close in response to signals like electrical changes. When the sodium ions enter the neuron, the cell's electrical potential becomes more positive. If the signal is strong enough and the voltage reaches a threshold, it triggers the action potential. More gated ions channel open, allowing more Na ions inside the cell, and the cell depolarizes so that the charges across the membrane completely reverse. The inside of the cell becomes positively charged and the outside becomes negatively charged. The peak voltage of the action potential causes the gated sodium channels to close and potassium channels to open. Potassium ions move outside the membrane and the sodium ions stay inside the membrane, repolarizing the cell. The result is a polarization that's opposite of the initial polarization that had sodium ions on the outside of potassium ions on the inside. The neuron becomes hyperpolarized. When the potassium gates finally close, the neuron has slightly more potassium ions on the outside than it has sodium ions on the inside. This causes the cell's potential to drop slightly lower than the resting potential. The neuron enters a refractory period which returns potassium to the inside of the cell and sodium to the outside of the cell. The sodium-potassium pump goes back to work, moving Na ions to the outside of the cell and potassium ions to the inside, returning the neuron to its normal polarized state.